Recording. Microphone is working. Okay, yeah, sorry. I no longer like the captions. It's kind of really, it's a visual blocker to me. So I think we'll have the AI generate the captions and put them to YouTube. I think it's going to get in my way right now, personally. Okay, great. All right. So if we're all here today, we should all be at this point officially enrolled in the course. If for whatever reason you still see yourself on the wait list, just come talk to me after class and we'll try to get that sorted. Today we're covering our very first chapter, Matters and Measurements, before we get into the content. If you haven't had a chance to join the Discord server yet, the QR code is up on the screen. Remember, once you join the Discord, you have to go into the Discord and confirm which campus you're on. Because I've already sent like 1 or 2 links in the Discord. So if you didn't see them, it's because you didn't claim your campus. So let me just show you what I mean. On the Discord channel, when you accept the invite, you'll be directed to the very first channel. It says campus selection. Under Carlbot, it says choose your campus. You're going to react the dog emoji for Woodland. And then once you react that emoji, you'll then get access to the Woodland specific channels. As of right now, I've only really posted one thing. Okay. Today, we also have our first workshop, aka that after lecture, we'll go into our lab session. There's a 15-minute break in between the two, so we'll probably take advantage of that. That way we can get some questions answered. But for today's workshop, we're not leaving this classroom, of course. So we'll go up until lecture 1:15. We'll take a 15-minute break, and then we'll just come right back here for the remainder of the workshop. Okay. All right. Like I said, we're starting our very first chapter today, Matter and Measurements. This particular chapter lays a lot of the foundation for the chemistry and science that we'll be seeing throughout Chemistry 1A. So first, I just want to define what chemistry is. Chemistry is defined as the study of composition, properties, and interactions of matter. Now, chemistry is often defined or described as the central science. And the reason for that is that it connects, chemistry as a whole connects to a lot of wide other branches of science, shown here, this spider web connection. This is straight from the textbook. It shows chemistry, of course, is central to understanding a wide range of scientific disciplines. And this particular spiderweb just shows the interrelationship between chemistry and a bunch of other fields. The immediate ones, of course, we know how chemistry can relate to chemical engineering, how it could relate to nanotechnology, chemical physics, nuclear chemistry, environmental science, and so forth. But individually, some of these fields do link to others. So what I'm trying to make the point here saying is that chemistry can be found at the epicenter of all of these scientific STEM fields and subjects. Now, historically, we used to refer to chemistry as alchemy, aka magic, right? Of course, now we know that alchemy is just one particular view of it. It's really just modern chemistry. But the way I want you to think about the history behind chemistry is pharmaceutical chemists or pharmacists. Way back when, pharmacists used to use stuff like natural herbs and remedies to help treat various issues. Now, they may not have understood the science behind why this particular tea leaf relieves constipation, but they understand that leaf relieves constipation. I will give you the leaf. Nowadays, our pharmacists and nurses and all the others, they're able to at least comment on the science behind those types of relief techniques. Hell, we can even think of someone, for example, Percy Julian. Percy Julian was an alchemist who almost exclusively worked on soybeans. soybeans, like literally those legumes. The idea way back when was, as an alchemist, Percy used soybeans to treat various issues within the body. I can take, for example, diabetes, just as a one example. Percy was the one who was like, well, maybe let's give you on soybean B, soybean C, B, D, blah, 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 blah. But as the field of chemistry evolved, Percy was able to further understand and study soybeans. In fact, Percy Julian can be thought of as the father of hormone therapy. Now, I use that example of diabetes just a while ago. I use that very purposefully, right? As we know, diabetes is just, ultimately comes down to an imbalance in the hormones. Percy Julian was the guy who ultimately was able to figure out, characterize soybeans, and link them to various hormone treatments. Now, of course, he would not have known the explicit details of something like diabetes way back when, but his work way back when really set the foundation for what we know today in the field of pharmaceutical chemistry. Now, the way in which Percy identified this effect or identified the structure is what's known as the scientific method. The scientific method is the general approach that any and all scientists will use when investigating a weird phenomenon, a concept, some observation, all that nice stuff. This diagram right here, this illustration from the textbook, shows the basic idea behind the scientific method. Now, it doesn't necessarily need to be as complicated as this figure looks, but I want to just talk about what the scientific process typically involves. Number one, you would observe some phenomena. You would be curious about it. For example, if we were to think about national parks, one of the most prevalent phenomena seen in water parks is not falling waterfalls. What do I mean by that? These are traditional geographical setup waterfalls off of a cliff, the water going all the way down. In some national parks, we do observe that the waterfall actually doesn't go all the way to the ground. In fact, something weird happens. The water will fall off the cliff into the waterfall, but for whatever reason, it'll just get pushed back. So it's sort of like an endless water wheel that doesn't actually touch the floor. From your observation curiosity, you're able to make a hypothesis, to form a hypothesis, right? From the hypothesis, you should be able to make a prediction. So in the case of that endless waterfall, why doesn't the water fall all the way to the ground? Well, one hypothesis could be the wind. Could wind be pushing the water back up such that the strength of the wind prevents the water from truly falling? If that's the case, if we were to somehow cut off the wind or turn it off, then we predict the water will fall as normal. Of course, on the scale of a national park, we're not really able to stop a waterfall, right? But we're able to perform an experiment on a smaller scale. These smaller scale experiments are just meant to be representations of the big, larger scale, so we try to simulate those conditions. But upon performing the experiment, we're able to make more observations. Now, at this point, we should have had some answers. Are the answers that we want? Not necessarily, but they're answers nonetheless. So we contribute to the body of knowledge. As we perform more observation, more experiments, we get more observations. We're able to test and get more consistent answers, and that's how observations become law. In other words, the reason why we know in national parks some waterfalls don't necessarily go all the way down, it's because the wind, the updraft from the wind, pushes the water back up. That becomes known and well understood. In other cases, the observations that line up with our experiments, but they're not quite perfect. There's no real scale or threshold, but we simply say that when our additional testing is needed, the hypothesis is simply a theory, not a law. All right. Now, in general, this is the process that's followed that any scientist in any field is going to use. They're going to make an observation. They're going to come up with a hypothesis. They're going to test the hypothesis. Upon testing the hypothesis, they'll either have a law or a theory, right? So the big difference that I want you to understand between a law and a theory is that a law describes or predicts with evidence. A theory, on the other hand, is substantial, but not comprehensive proof. So it's a very small distinction between the two ideas. And, a lot of students will ask, well, when exactly does a theory become a law? To be quite honest, it becomes a law when basically everyone agrees with it, right? When we say substantial but not comprehensive, using that waterfall analogy as an example, someone might say, yeah, you have a lot of evidence that the wind is what the cause is, but could it be that the change in air pressure or the temperature as we go from the top of the waterfall to the bottom has an influence on, well, the water disappearing, right? So that's a situation where you'd have a theory, not necessarily a law. Now that we understand a little bit more about the scientific process and the method behind it, I'd like to talk a little bit about the nature of matter. And over the course of this class, we're going to encounter different phases of matter, all shown here: solids, liquids, and gases. Now, for the purposes of this example, I'm going to use water. Now, we know, of course, as a solid, so it's going to be difficult to see the screen based on how I thought, so I recommend you sit over there. We know as a solid, water exists as an ice cube, right? Liquid water, and of course, gaseous water is just steam. The different states of matter have different characteristics. Solids, for example, have a fixed shape and volume. That means no matter the size of the container, whether it be a flask, a jug, a cup, or even your awala, ice cubes have a defined shape and volume, right? So traditionally, ice cubes are solid, but different ice molds may have different shapes, but the idea is the same. In a solid, these particles are fixed in terms of their shape and volume. In the case of a liquid, however, liquids take the shape of the container. You pour water from a jug into the awala, right? The water, if you were to collect that water as is in the awala, it would take the shape of the awala bottle, right? And it has a horizontal surface and a fixed volume, aka 100 mils of water is 100 mils of water, whether it's in an awala, a jug, a milk carton, or a cup. And then finally, we have a gas, right? Maybe water vapor isn't the perfect example here. Let me use an example of something such as Febreze. We spray Febreze. We see the particles probably immediately upon spraying, but they eventually disappear to the naked eye. It's because those gas particles expand to fill the container. You can see here in this case, it has been trapped in the flask. In the case of something like Febreze, it would expand to fill the entire room or just the closed system that you have. All right. There is another state of matter, one that is commonly seen, but not yet, I would say, introduced into the general curriculum. We have plasma. Plasma is a combination of all three states. Combo of at least two, let's say that. At least two states. One of the best examples for plasma is, of course, blood. Blood, we know, is a liquid substance, but within the blood itself, we have solid particles. We have those red and white antibody cells or anything else that's found in the blood. It's not just pure liquid. Now, that actually brings up a very good question. If blood is a combination of multiple states, where in the case of blood, it could be literal liquid blood, it could be those physically solid white and red blood cells, it could even be other slightly things that are found in the body, iron, for example. The question then becomes, what is the difference between a pure substance versus a mixture? To answer that, let's define each of them. In the case of a pure substance, these are examples of elements that cannot be broken down. At least not chemically, anyway. What does that mean? If you've ever passed a construction site, you know they, of course, use things like metal, zinc, aluminum, all that stuff. If we think of, for example, a sheet of aluminum, of course, we're able to cut the aluminum with different tools and equipment. That's a case of breaking it down physically. But when you break or cut that aluminum sheet, it's still aluminum. So that is a situation where we have a pure chemical that cannot be broken down chemically. Right? So I want to make that distinction clear. Similarly, for pure substances, we might also see compounds, which is two or more elements together. In a fixed composition. An example of a compound, most of us may know this one, H2O. Many of us are able to recognize H2O as water. This is a situation where the water is comprised of both hydrogen and oxygen, specifically 2 H's and 1 oxygen. Another example that you might see in your day-to-day, table salt. It's okay if you don't know the elements, if you don't know that this is hydrogen, oxygen, and so forth. We're going to talk about that eventually. But I just wanted to show you that these are some things that you do have experience with, at least in your day-to-day. In the case of a mixture, as the term suggests, it's a combination, it's a mixture of different things. You can have a homogeneous mixture, which is ultimately defined by its uniformity. This is an example. An example of this is salt water. There is salt, there is water. Together, the body of water is salt water. We're not looking for a perfect 50-50. We're just saying that this water has another chemical in it, and for that reason, it's called a mixture. Then we have heterogeneous, which is not necessarily uniform. What do I mean by that? Well, an example of this is lemonade. If you've ever made lemonade, you know that, of course, it's a mixture of chemicals and ingredients, water, sugar, lemon juice, but not all chemicals are added in the same amounts, right? You don't necessarily use the same amount of lemon juice as you do water. Otherwise, you're going to get a really tart lemonade. Similarly, you want to use a little bit of sugar to give it that sweetness, but not too much, not to overwhelm the senses. These ideas help us understand and talk about chemistry and matter in very different ways. Now, how does this affect the various scope of chemistry? Let's look at the different domains of chemistry. The first one is macroscopic. These are things that we can see or touch. An example of this is ice melting. We're able to see the ice condense with sweat on the side and turn fully into liquid water, melting. We're able to touch it and feel the solid ice as well as the wet liquid dripping off of it. We then have microscopic, which is simply invisible to the naked eye. The macroscopic domain of chemistry just takes one further look at what we are able to see and touch. For example, using ice melting as using ice melting, we can see macroscopically the ice melting. What we cannot see, though, are the water particles loosening. We cannot see the specific particles within the ice cube loosening to form water, right? And then finally, we have the symbolic domain. The symbolic domain is, as the term suggests, it's just a representation of what we're looking at. Throughout our examples here, ice melting, water particles loosening, the symbol that we're really talking about here is water, H2O. Now, the best way to think about these domains is kind of like you would describe a city. You walk into a city, you see all these large buildings. Those large buildings would be macroscopic. All right, what about microscopic? Well, in the case of buildings, I could argue the brick, the cement, the mortar that was used. You know it's there. If you really went digging, you could find it, but you're not immediately able to see all of that stuff. And then what do you guys think would be the symbolic representation of a city? Does anyone have any guesses? A map. A map, M-A-P. A map is a symbolic representation of the city where you're able to, on the map, see the buildings. You know that in the buildings is brick, mortar, cement, blah, blah, blah. But the map just represents a symbolism of the city as itself. Another avenue in which we see this is with ice, for example, at Antarctica or the North and South Poles. This image right here shows all of the major domains that we could expect to see in water. We, of course, know there are water particles in the liquid. We can see the iceberg. We can see the clouds, which we know are comprised of different chemicals, water vapor, et cetera, et cetera. And we also know that there is moisture in the atmosphere. All of this together is what gives us the language to talk about chemistry, to talk about it within context of real world scenarios. Something that you're going to see a lot of times during this semester is how I try to relate things that we encounter in class to things that you might see on a day-to-day basis. But how does that translate? I mean, this whole time we've just been talking about water. Of course, it's easy to say, yeah, I know what water looks like. I know that water has that type of blue tint in this regard. Maybe it's colorless in the cup, but I know what water is. What are some other ways that we can describe chemicals using this language? For that, we turn our attention to physical and chemical properties. Starting with physical. This one's the more obvious stuff. These are characteristics that are observed that can be observed without changing composition. An example of a physical characteristic, a physical property, is color. The walls are cream/beige. The door is brown. The exit route sign is red. The top of my screen is blue. These are all observable physical characteristics that don't require you to change anything about it. Similarly, melting and boiling points. PTS is my shorthand for points. The boiling point for water, for example, is 100 degrees. The melting point, 0 degrees. These are set things. These are set points. But when we talk about physical properties, a consideration does come up. Are we referring to an intensive property or extensive? Well, first thing we want to know is what's the difference? Intensive characteristics are independent of the amount of that chemical present. So an intensive characteristic is an inherent characteristic. And this goes back to our classic example, color, boiling point. Whether you have a cup of water, a jug of water, a whole pool full of water, the boiling point is the same. It is an inherent characteristic. It is intensive. It is independent of the amount. What about extensive? Well, if intensive is independent of amount, then extensive is dependent on amount. What's an example of this? Mass. I don't weigh the same that I did 5, 10 years ago. My mass changes. Although a physical characteristic, you can see how big I am. The exact number depends on how much of is there. Depends on the amount. Similarly, volume. 8 ounces of water is different from 16 ounces of water. Depends on the amount. And remember, in both cases, 8 ounces or 16 ounces, the boiling point is the same. Now on to chemical properties. Oh, did not have a line for that one. Yeah. Chemical properties can be broadly described as behavior during chemical changes. An example of a chemical property is flammability. Another example of a chemical property is rusting. Different metals rust at different rates in different environments. The environment plays a huge role, so you cannot quite say all the time, aluminum will rust in XYZ manner. Depending on the environment it's in, it could be different. So chemical properties, I like to think of as being those more abstract ideas, things that you can't quite put a number on. In other words, I cannot say wood is 1.92 flammable. You won't describe it like that. You wouldn't put a number to things like that. you would just say, yeah, wood is flammable. That's it. So you can think about it in that way. Things that you can't traditionally put numbers to are chemical properties. So what does this tell us about the different ways in which chemicals behave? We have physical changes and chemical changes. An example of a physical change is, well, wax melting. Sugar dissolving. What's an example of a chemical change? Cooking. Digestion. Striking a match. Do we have any questions so far? Okay. Now that we have, for lack of a better phrase, an abstract view of what chemistry is, we've talked obviously about where is it? We've talked about its origin. We've talked about how ubiquitous it is. We've talked about the scientific process, the method behind it all. We've even spent a little time understanding the very basics of chemistry, understanding the language that we use, solids, liquids, gases, pure mixture. We've even talked about domains of chemistry and touched on these physical and chemical properties. Let's put some numbers in it. Let's talk about measurements and units. Throughout Chem 1A, you will encounter the big four measurements. You will see situations where you'll have to measure length. Situations where you will have to measure the mass of an object. In some experiments, you're going to record the time it takes for a reaction to occur or for something to happen. And this should come as no surprise. We'll be recording temperature at different states. These are the big four measurements that we will encounter in 1A. They aren't the only ones that you will see in general, but these are the big four that I expect you to know. So if these are the measurements, what are their units? Well, take, for example, length. American or imperial or metric system, you have stuff like you can measure in terms of yards, miles, centimeters. We use what's known as SI units. Where the SI stands for International Standard. They just put the S first. The SI units are what we will default to. In the case of length, it'll be meters. In the case of mass, it will be kilograms. In the case of time, it will be seconds. In case of temperature, it will be K as in Kelvin. Kelvin is most likely the one that you have not seen or experienced before. And we're actually going to talk a little bit about the Kelvin temperature once we finish up this little thing on SI units. Now, like I said, these are not the only ones you will encounter in general. So I just wanted to show you some other examples. We've already talked about length, mass, time, and temperature. Some of the others that you might encounter, especially in the Chem series in general, not just 1A, is electrical current, which is measured in amperes, the amount of a substance, which is measured in moles, and the luminous intensity of a substance, which is measured in candelas. Okay. Let's talk just a little bit about Kelvin. To convert from Celsius to Kelvin, the Kelvin value will be equal to the Celsius value added to 273.15. So for example, 25 degrees Celsius is equal to 298.15 Kelvin. We simply added the 25 to the 273.15. Similarly, to go from Kelvin to Celsius, it's really just the opposite. It'll be the Kelvin value minus 273.15. If, for example, we have 300.15 Kelvin, that's going to be, of course, equal to 27 degrees Celsius. I do expect you to know how to convert between Kelvin and Celsius. Please note that unlike many conversions, this is just an addition or a subtraction. So on their own, these units, they are instructive, but they're not quite actionable. Meaning, I can go get a ruler, I can go around and measure the length of every table in here. I can go around and measure the mass of every chair in here. I can measure how long it takes me to do all that stuff. I can even measure the room temperature. These are all things that I can collect directly. A ruler for length, a scale for the mass, a stopwatch for the time, a thermometer for the temperature. But upon getting these simple units, what can we do with them? We can get further derived units. Derived units are brought about by mathematical operations on those simple units. The biggest example is density. Density is equal to the mass of a substance divided by the volume of a substance. And the units Well, this is where that derived word comes from. We know the unit for mass, the SI unit for mass is traditionally kilograms. Not in the table shown, the SI unit for volume is centimeters cubed. And that fraction alone tells us this is the unit of density. Mass over volume. So now that we understand the benefit of collecting these measurements directly, we understand that we can then manipulate these measurements into different formulae. What do the numbers actually look like? Uncertainty and significant figures. We're going to first talk about uncertainty. Here, we have a graduated cylinder that we have filled up, right? It's a cylinder because it's that tall cylindrical shape, and it's graduated because there are graduations on it referring to the different numbers. We see here that it goes up in terms of 1, 1, 2, 3, 4, 5, and so forth. We measure the volume of a liquid in the graduated cylinder, and what we see is this sort of curve. You will never see a straight line. You're always going to see that curve. That curve is known as a meniscus. Meniscus. And looking a little bit further at the meniscus, zooming in a little bit, we're able to see that the meniscus lies quite squarely between 21 and 22. Okay, so if we were to take a guess, I'd probably say this is around 21 and a half. But that's exactly what you're doing. You're guessing. You cannot say with absolute certainty this meniscus right here is exactly 21.5. You can't. There are no measurements on the cylinder that tell you that. You're making a guess that it looks to be about half. So what do we do in this case? 21.5. We just go one more decimal place. By going one more decimal place and saying something like, well, I guess or estimate this to be 21.58. Here's what I am telling you, the reader. I am telling you, the reader, hey, I'm pretty confident it's around 21.5. But guess what? Give me a margin of error of 0.01, that second decimal place. In other words, there is a chance this could be 21.56, 21.59, 21.51. What I am certain about is a 21.5. So what does that mean? Whenever we're recording measurements, whenever we're reading values, we're able to write down values up to a certain point, and then we will guess the last decimal place. And it all depends on the equipment you're using. This graduated cylinder is incredibly limited. It just goes up in 1 mil increments. But take, for example, a ruler that has graduations within it. All right. Now you're able to say, okay, well, if I want to measure this point right here, I look at my ruler and I say, hey, this looks like 1.7. This is the extent to what I can guess. Let me just go one step further to make it clear. There's a level of uncertainty here, 1.77. And the beauty of this is that it sort of identifies any sort of discrepancy between you and your neighbor. I might see this as 1.71. Your neighbor might see this as 1.79. You both agree about that 1.7. Where the uncertainty comes from is that last decimal place. But this is just one reading. This is just one graduated cylinder. What if we were to take multiple measurements? When dealing with multiple measurements, we now have to contend with another factor: accuracy versus precision. To understand the difference between the two, I want you to think about a dart board if you ever threw darts. We all understand the basic idea of the dart game. The goal, of course, is to get into the center as close as you can. You'll be the winner. More often than not, you're never really going to hit it perfectly every single time. So let's define what accuracy and precision is in the concept of this dart board. Right here in the center, what we have are precise darts. Precise meaning close to true value. But it's not accurate. Why is it not accurate? Because we know the center is where we're aiming for. So whoever it was that threw these darts, they got a good hand. Their measurements are pretty close to one another. The darts are really close. But they're not accurate. They're just close to each other. What about this one over here on the far right? We have here a situation where this person threw darts nowhere near the center, not accurate at all. And they're not at all close to one another. In fact, there's some distance between them. And here in the very, very first, we have someone who threw darts perfectly. All of them ended up in the center. This is both accurate and precise. So this page, this slide right here, I shouldn't say slide. This page right here tells us a little bit about how we measure those simple units. It tells us when we measure these units, there is a level of uncertainty behind them. It tells us that if we take multiple measurements, sometimes our measurements may be accurate, sometimes they may be precise. We want them to be both. So now that we understand a little bit more about actually performing these measurements, actually getting the data, I'd like to talk about significant figures. as the term suggests, significant figures. These are figures that are, well, significant. How do we determine if something is significant? Well, it depends on the context. If I go to a furniture store and I ask how much for a couch, they'll tell me, oh yeah, it's around $1,000. Okay. I go to the couch, I look at the marker and it says $989.52. But the salesperson said, yeah, you should expect it to be around $1,000. Which one do you think is the more significant quote? A 989. Why? Because this 1,000, really, that's just an estimate. So that brings in an important aspect I want you to understand about significant figures. Significant figures are exact. Going to the grocery market and being told, yeah, for a pound of meat, it's going to be about $50. That's not significant. There's a chance it could be $40. There's a chance it could be $60. There is a chance that it could be $30, and then tax will raise it to 50. But if I go on FedEx and I say, hey, my package weighs 1.1 pounds, they'll tell me, okay, based on that, your estimate is $130.52. That's significant. That's exact. So how do we determine what's significant or not? We look at the rules of significant figures. There are 4 rules. Number 1, all non-zero digits are significant. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, all of those. They're all significant. All non-zero digits. Leading zeros are never significant. The best example I can show you about this is, say, for example, the table that you're at, the bench that you're at, it comes in at a measure of, I don't know, let's say less than my wingspan. Yeah, so let's call it 6 feet. What we're trying to say here with leading zeros is if we put zeros in front of the 6, does that really affect our description of the length? No, not really. I mean, 0, 0, 0, 6 is the same thing as just a flat 6. Those zeros were not needed. They're just not significant. Number 3, captive zeros are always significant. An example of a captive zero is in 101, where the 0 is literally being held captive between significant digits, 1. And then number 4, trailing zeros are, and there are a couple, there's actually two adages. Number one, trailing zeros are significant if there is a decimal point present. PT is my shorthand for point. Trailing zeros are ambiguous without a decimal point. All right, let's take a look at what this means and how you would see a question on, well, a question about this would appear on an exam. Determine the amount of sig figs in, and we have a couple of questions. Sig figs is a shorthand for significant figures. First up, 0.00832. 0.00832. All right, let's look at our rules. Number one says all non-zero digits are significant. Okay, so immediately we know 8, 3, and 2 are significant. Check, check, check. What about those initial zeros at the beginning? Well, let's try to describe what they are. They're either going to be trailing, captive, or leading. Does any brave soul want to tell me what they think these kinds of zeros are? Leading. Yeah, I heard that. Leading zeros. Why? Because they're in the front. They're leading the group. In the case of number one, this only has 3 significant figures. None of those zeros are significant. All right, number 2, 1,300. All right, pretty quickly we should know the non-zero digits are significant, the 1 and the 3. The question is, of course, about the zeros. Leading, captive, or trailing? Trailing, okay? Trailing has an adage. Trailing says they're significant if a decimal point is present. Is a decimal point present here? No. So it is ambiguous. Now what, pray tell? But what if I had switched this to 1,300 points? How many significant figures are in this number now? 4 significant figures. All right. What about 103.00 times 10 to the 4? Okay, well, we know that the 1 and the 3, they're significant. They're non-zero. That's easy. Get that out of the way. This 0 in the middle kind of gives it away. It's in the middle of something. It's in the middle of 2 digits. This is a captive 0 right here. This captive 0 is significant. What about these trailing zeros at the far end? Trailing zeros are only significant if there is a decimal point present, which there is. So significant, significant. What we have here is 5 significant figures. Does the times 10 to the 4 count? Nope, it does not. This is just the easy stuff. This is me telling you, here's a number. Tell me how many significant figures are present. That's not all you're going to do in this class. Yeah, is there a hand? What's up? That's a very good question. Ultimately, I would say it depends on the wording of the question. You know, this is just asking you determine the amount, right? I'm giving you flat numbers, so you should take the numbers as is. If I were to have said instead, below are volume measurements of different bottles of water, then that would be a level of uncertainty in the number. So it depends on the context of the question. This one is just a, here are some numbers, take them as is, tell me how many significant figures there are. Good question. Good question. So when are you actually going to get to use significant figures, or at least when is it most important? When dealing with arithmetic. I think I spelled arithmetic wrong. Arithmetic. With sig figs. That W slash is my shorthand for with, W-I-T-H. There are two categories of arithmetic that you will encounter in this class. The first is addition and subtraction. Whenever you add or subtract numbers, you're going to round the number to the least amount of decimal places. The other category is multiplication and divide. In this case, you're going to round to the least amount of significant figures. Let's take an example of what that would look like. We have here 1.0023 added to 4.383. So this is just a simple arithmetic operation. We're adding them together. I already have the answer at the ready. It's the full answer is 5.3853. This is the full answer if you were to write it out on your calculator. I would ask you on an exam, please write your answer to the correct number of significant figures. All right, how do we do that here? We look at our rules for addition and subtraction. We round to the least amount of decimal places. For the first number, we have 1, 2, 3, 4 decimal places. In the second number, we have 1, 2, 3 decimal places. So how many decimal places should we actually have in our final answer? 3. We go 1, 2, 3. After the third number is when we decided we should round up or down. This is 5 and 3. Do we round up or do we round down? Down. This becomes 5.385. What about in the case of a multiplication? We have 0.6238 times 6.6. This is equal to 4.11708. This is how it'll spit out on your calculator. This is multiplication, so we're going to round to the least significant figures. Let's look at our options. Over here, we have 6.6. This one's easy. It's just two significant figures. They're both non-zeros. There is no question about captive, trailing, or leading. In the very first number, we have 6238. Is the zero significant? No. So how many significant figures do we have? 4. The rule says the answer must be written to the least amount of significant figures. We want 2 significant figures. Looking at the number in the US education system, we count from left to right. Our first significant figure is 4. Our second significant figure is 1. Stop. After the second significant figure is when we decide if we should round up or round down. This is 4.11. Do we round up or do we round down? Down. This becomes 4.1. Any questions? Okay. The next measurement topic we'll be talking about is scientific notation. Scientific notation takes on a very specific order. We have some number times 10 raised to some other number. The rule about scientific notation is that this number over here on the left must be between 1 and 10. Meaning it can never be 11. It will be 1.1. It will never be 0.9. It will be 9.0. We're looking for the number to be between 1 and 10. Up here, this can either be positive or negative and represents the number of jumps. What the hell does that mean? Number of jumps. Well, the best way to get the point across is let's do an example. Right here we have 1, 2, 3, 4, 5, 6.7, 8, 9. All right. We want to put this into scientific notation. We want this to resemble something times 10 to the something. We are going to jump the decimal place in a direction that gets us to that point. What if we jump to the right? Oh, well, that doesn't quite lead us. If we keep jumping, we don't go between 1 and 10. What if we jump to the left? Okay, still not enough. Still not enough. Still not enough. Still not enough. Oh, wait. If we keep jumping, eventually we will get 1.2345678 9. This meets our requirement that the number in front must be between 1 and 10. We could not have stopped at the 2 because this would be 12.345, which is not followed on our rule. We could not have gone one more and gone 0.12345, blah, 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 because it needs to be between 1 and 10. So we specifically jumped 1, 2, 3, 4, 5. Times 10 to the 5. What about the positive and negative? Well, in this case, the 5 is positive. It is positive when you jump to the left. What about the situation where you jump to the right? Well, let's look at that, an example of that. 0.0001235. I kind of gave it away, but obviously in this case, we're going to jump to the right. We're going to go jump 1, 2, 3, 4, 5. Am I correct? See a couple of shaking heads. I want someone to say it. No, I am not correct. Why? Because if I jump right here, I'll get 12.3. That's not correct. So I'm going to only jump 1, 2, 3, 4. This is going to be 1.2345. It's going to be times 10 to the 4, representing 4 jumps. And it's going to be negative to represent that I jumped to the right. Does anyone want to take a guess why scientific notation was developed in the first place? To condense how much you have to write. Scientists are lazy. We now have computers and word processing software. But 50, 60 years ago, when a scientist wanted to publish something new and novel, guess what they did? They wrote a letter to the respective publishers. It literally used to start with "Dear Sir" or "Madam," and they would handwrite everything. Maybe if they had a typewriter, they would use that. But who the hell wants to keep writing 0.000 over and over and over again, especially if it's a number that appears a lot of times? So it's much easier to just write 1.2345 times 10 to the negative 4. It's easy for us to understand. And the other big reason, it simplifies it. Right? Look at the zeros. I don't know about you, but sometimes when I quickly scan these numbers, the zeros don't always appear to me immediately. I, for example, see that. I might sometimes think, is that 2 zeros? Is that 1 0 if I'm just skimming a document? By putting it in this form right here, you're making it clear, oh, this is a number we got to pay attention to. Whatever you're timesing 10 by. It is 1:15. We're going to end lecture for today. We'll take a 15-minute break, and at 1:30, we will be right back in here for our workshop. See you guys in about 15 minutes. If you want to stay here, that's fine. Like I said, I'm going to give everyone that 15-minute break.